Hi, good afternoon or good morning, depending on where you are in the globe. But today, ZP, we're going to do a quick webinar on technologies for academia. Um, it won't be the kind of webinar where it's all talk. I mean, we do talk and we will talk quite fast. But I want to just say that I've got a host of technologies in front of me, and I will be going through a few of these things and sort of illustrating with demonstrations about what it is. When I make it a point, I'll try and illustrate it with some actual technology as well. So just to say, this is not all talk this afternoon. So even though you see the dreaded slides will transition quite quickly, and we will be definitely doing some demonstrations as well. So the purpose of this afternoon is really to talk about technologies for academia. It's really about creating impact. So I have slides on this one. I'll make the points as I go along. But really, I do not want academic research just to finish at the point where somebody does a scientific paper. The conclusion is like the death nail in that technology, because that's the point at which when somebody writes a conclusion in the paper, that's essentially the kind of the end point. But actually, governments and funders are looking for more like impact these days. What it is what is it your technology is going to do for society? And another way of phrasing that question is, can you get that technology actually out of the lab? So let's talk about creating impact. And because this is VP, we'll be talking specifically about electrochemical sensors and biosensors. And I think those two terms really come underneath this title of electro-analytical chemistry. So I will be talking in the field of electro-analytical chemistry, but I will be talking about a little bit about wearables, but not much. I will be talking mostly about something called point-of-care diagnostics, or also point-of-need diagnostics as well. And I'll be using screen-printed electrodes and a very new sort of type of potentiostat for illustrating and doing demonstrations and talking about or illustrating what I want to actually say this afternoon. So with that said, I have a few slides here. So we'll talk about the current situation that I see in academia. And this current situation is a past situation, the current situation, and it hopefully won't be the ongoing situation. We'll talk about point of care, point of need testing. So point of care diagnostics is a term that you could strictly apply when it comes to medical. So point of care diagnostics could be a lateral flow strip for COVID-19. That's when everyone became really familiar with take a drop of blood, put it on this lateral flow strip, put a bit of buffer on that, and then it would kind of flow up the lateral flow strip. And depending on the color change on those bands, you were either positive or not. So people are familiar with point of care diagnostics. I'll do a point of need testing this afternoon. So I think for me, point of need just means it's like point of care, but it's not necessarily medical. So, for example, I'll give you a point of need test in the food industry. A lot of the world, by the way, is going in. There's more testing going on than ever. In the first instance, it's probably often point of need testing, and everyone wants continuous, but continuous is definitely harder. A good example of continuous is CGM, continuous glucose monitoring. Now, this is not really I do separate webinars on CGM or continuous glucose monitoring and wearables. So I'm not really going to talk about that this afternoon because it's basically 45 minutes just in itself. I will talk about screen printed electrodes, um, how actually there's basically an oversupply of screen printed electrodes. If you're not sure what I mean by screen printed electrodes, here's a beautiful one from ZP. Um, there's an oversupply in the market, and it's actually really it drives down costs, but it actually also drives down quality as well. And it's actually impeding the impact or the translation of research out of the lab. So many startup companies or so many labs I find are actually troubleshooting screen printed electrodes because they don't appreciate that um, those electrodes are never going to be reproducible. Not because they can't be, and I'll try and illustrate what I mean by that today. So let's talk about reproducibility. At ZP, we do make a very reproducible screen printed electrode. A reproducible screen printed electrode means that we can translate research into products. It leads to simpler assays, and it leads to no calibration. And it's this sort of complex assays and the need for calibration that are sometimes holding back the translation of electrochemical assays into products. I'll talk about cloud-enabled potentiostat. So when I mean a cloud-enabled potentiostat, when we first launched this, we call it the SEER potentiostat, the Sensi All potentiostat. When we first released it, we released it as a platform for the translation of electrochemical assays into products. But now actually we've migrated it almost backwards through the research pipe, and actually we've turned it into a potentiostat, so we can do amperometry, open circuit potentiometry, impedance spectroscopy, linear sweep voltammetry, cyclic voltammetry, square wave voltammetry. But it's not like any potentiostat that's necessarily been seen before, because actually it looks much more like a medical product, and much more like a product that you could actually give to a consumer, because it does not look like a scientific instrument. And this looking like a scientific instrument is actually what's holding back people's imaginations, actually, when it comes to translating their ideas into products and essentially having an impact. So I'll talk about cloud-enabled potentiostats. I'll talk about normal laptops. What I mean by that is this particular potentiostat is actually in Bluetooth connection with my phone. So it's really amazing, actually, that it's not the end of laptops, let's say. I mean, they're still useful, and I'll use one to present this afternoon. But the idea that you have to have a laptop in order to run a scientific instrument, it's not the case anymore. In fact, laptops were seen as a revolution because they already reduced the tower down to something much smaller. And now, actually, no, I can run this scientific instrument off my phone using a Bluetooth connection to my phone. And the great thing about phones is they, or smart devices, I should say, is they provide automatic, well, not automatic, but they provide connection to the cloud as well. So you'll see that this afternoon as well. So it's smartphone only, no menus. So when I say no menus, part of what I'll show this afternoon is that if we want to make this device do something, we're actually using QR codes. So we're scanning QR codes and actually so we can go between different methodologies by using QR codes. And I say cloud enabled, so I'll show you that we have methods and we have what's called a data pipe. Everyone these days should think of themselves as a data scientist. If you sort of identify, let's say, as an electrochemist or a biosensor developer, or an electro-analytical scientist, we're really just part of the data science community. And so we're all about actually having methods, getting raw signal, putting raw signal through data pipes and turning it into something that's actually useful to society. So, for example, if you're going to make an enzyme measurement, and I'll choose one that, illustrates my point. So, in fact, if I make an enzyme measurement, and it could be a glucose sensor, real doctors and nurses do not want to see your amperometric signal. They want to see glucose concentration. If you're in a hospital and you're measuring somebody's blood for potassium, they do not want to see potential, which is what an ion selective electrode would give. They want to see actual potassium levels. So I'm showing you an instrument this afternoon that is both a potentiostat, it's cloud enabled, and because of the pipeline, it actually converts signal into final concentration. And that's the gap that's the final gap, basically, that most papers actually finish with raw signal, which is, it's almost useless to anyone outside of the electrochemistry community. So we'll talk about that this afternoon, which is then part of translation. So if you've never heard, I'm sure you have, but there is a term out there called technology readiness levels. So when you first have an idea, that's technology readiness level number 1. When you're thinking about it a little bit, that's technology readiness level number 2. When you go in the lab and kind of do some lab work and say, oh yeah, I've got a signal here versus concentration, then you're at technology readiness level number 3. And that's where most academic research actually finishes. But and this would be a robust product, let's say, to get to this kind of robustness, that's more like a technology readiness level number 9. So we're going to talk about how to go from 3 upwards to 4, 5, 6, 7. 9 does take a few years, but we'll talk about that this afternoon, and we'll talk about the valley of death. This is not something in the US, not Death Valley, but the valley of death between where academic research finishes and where impact and translation into products that impact the real world starts. So I'll talk about that as well. I'll talk quite quickly because I want to be efficient. We're already 10 minutes in. So if you read a paper around electro-analytical science today, there'll be a title, there'll be an introduction, so checkbox. There'll be an explanation of the mechanism, maybe, what is the science that's giving me this signal? There may be how to repeat my experiment, an experimental section, tick. There'll be some raw signal. There may even be some signal versus concentration. So signal versus concentration is one of the first steps on making a commercial product. And you may even get a calibration curve out of that. And in this particular case, the authors have tested some real products. So they are trying to do the development of a product in the paper like this, where they're actually measuring the capsaicin in chilies. And there's I'm going to put, and then it finishes with a conclusion. And this papers like this would always finish with a conclusion, and that's almost a conclusion of where this research is actually going to end up. But of course, it's a very practical paper. It's trying to measure something in a real world product, but it just finishes with that. I'm sure if you're working on analytes for human health, you really want it to end up actually being in a product. If you're working on analytes for measuring the environment, you want that ending up in a product. This is a very similar paper, but it's the same story. So we've got John Hart here at UWE, the University West of England. Title, great. Abstract, introduction, materials. How can I do it? Here they actually screen print an electrode. Signal versus concentration, and also how signals are affected by pH, and then a conclusion. So the papers have different titles, but actually they're both using essentially screen printed electrodes, and they both go through similar sections in their paper. And so the problem that we're solving at Zimmer and Peacock is this: that I was talking to a colleague at Manchester Metropolitan, and I think he told me that in fact papers like this, there are 25,000 papers like this produced per annum, which is great, because if you were me and you want to see if you can make a new sensor, if you Google the analyte of interest and you put voltammetry in that Google search, there's always a paper. Why is there always a paper? Because we're probably producing 25,000 papers per year. So what's the problem we're trying to solve? The problem we're trying to solve is there's 25,000 papers per year. How many of those are actually translating into products? And I'm going to talk about why I think there's the root cause of that, and then a biased opinion from me how we solve it. So 25,000 papers produced a year. They're all going to go into the shelf. And at ZP, we're trying to solve this because we actually want these to actually have a real world impact. And so does the government. The government is now making people actually demonstrate that their science has some kind of impact. Well, getting it out of the lab and into a clinical trial, or getting out of the lab and just actually having some doctors run it on real world samples, or getting out of the lab and actually using it in water testing, or getting out of the lab and using it in food quality, food safety, that's demonstrating impact. And normally that would be quite hard, but with the technology that I'm just going to show this afternoon, then it becomes much easier. In fact, I'm going to do a demonstration just to start with. So rather than do a lot of talk, let me change cameras for a second, and I will take you through this. So this is the potentiostat. This is the Sensi-All potentiostat. I can do cyclic voltammetry on that. In fact, there we are. I just scanned square wave voltammetry. I can do cyclic voltammetry on this potentiostat. It says on here, device connected. What it's actually connected to by Bluetooth is to this particular instrument here. What I'm going to do is I'm going to put a clean sensor in this. So let me just take this guy out, and I'm going to put a sensor into this. So now I'm super biased. These are really good screen printed electrodes, and it's the gluttony of screen printed electrodes that's on the market that's really holding back a lot of research. Now I'm going to actually just going to change from doing a scientific experiment to doing a real world experiment. So I'm just going to go and scan over here, which I've done. So this is now changed the look and feel of this particular app. It's the same app, it's Sensi-All, but now it's actually going to be doing a sort of a measurement. But showing will help you understand, let's say, a bit better. I'm going to take a real world sample. What I love about electrochemistry is samples in electrochemistry do not have to be particularly clean. This one's slightly orangey and it's a bit bitty. In fact, so I'll take that sample and I will bring it up. What's the other thing we like about electrochemistry? We like the fact that it only takes 50 microliters. Well, it takes much less than actually. But I'm putting a 50 microliter drop onto that. And in fact, I need to give this a name very quickly. So I'm just going to give it a name. Now, the reason I'm giving it a name is because I want to show you that this is, I'll call it tab 53. Well, actually, I called that 63, but that's fine. Yeah. The reason I gave it a name is because I want to show you that actually I can retrieve that data in a little bit in a cloud system called Julie. Actually, when it comes to that, something I sort of forgot to do, but I may actually do it just really quickly now. So sorry to kind of slightly change course for a second. So I've got a result on my phone, and I will emphasize that point in a minute. If you look at what we're doing, what we're really doing is borrowing from one of the most successful biosensor technologies in the world, which is a glucose strip. So let me just do this very quickly. If any of you are ever wondering why you should be interested in a webinar like this, glucose strips are the kind of demonstrative technology for this. So in fact, I've just measured my blood glucose. It's 93 milligrams per DL. What did you just learn from these two demonstrations? You just learned that you don't need much sample preparation because it's a drop of blood. How many optical systems can you actually do that with? You learned that actually we didn't need much sample. This used 300 nanoliters. This used 50 microliters, and they were both fast. And by the way, they're both low cost as well. Now, let me go back to what I was actually meant to be talking about, which is I've got a result on my phone. The fact that I've actually got a result on my phone, that raises this to a higher technology readiness level. It says micromolar 482. Now, what I want to do is I want to share my screen with you. So I will just do a quick share here. And the reason being is on my phone, it says a couple of things to me. It says upload complete and it's got the concentration. And I called it tab 63. So I'm just going to go into, so understand that upload complete means something. It means that actually the data went up. So it's cyclic voltammetry that I ran, but I'm sorry to cause any, mayhem here, but nobody likes cyclic voltammetry. So what did we do to it? We actually processed the peak. We found out its peak height and we turned it into concentration. So this is the gap that is missing. If you are doing electrochemical experiments in the lab, or you're just interested in being an entrepreneur, or you're actually just interested in having more impact from the voltammetry experiments that you're doing, or the EIS, the electrochemical impedance spectroscopy experiments that you're doing, or maybe the amperometry experiments that you're doing, if you want to have more impact, then this is how we do it at ZP. So I mentioned a data pipe. You are a data scientist. You happen to be working at the front end of collecting data, but the bit that we kind of are not being taught, either graduate or postgraduate, is actually we're maybe taught. We have to self-teach ourselves these days. Is actually we are all data scientists. So in fact, there's a data pipe in this, and what this data pipe is doing is it's actually saying, do you want to filter this data? Is this data messy? Well, actually, my data wasn't that messy, but I did do a low pass filter on it. There's lots of filters available, low pass filters, etc. Moving average is in there as well. I flipped the data around the y-axis. I cropped the data. I then told it to extract values. I told it, give me peak height and look in this window here. Look in the potential window around 250 millivolts. With a 300 millivolt sort of breadth of window. And the last, but but important part is fit to a formula. And there's all sorts of formulas available, but I actually did this weird one here, double log. And here's the kind of sensitivity and coefficient. Oh, and by the way, I also did dilute my sample by 1 in 10. So I also told it that. Understand what that means is, if you're doing a scientific paper today, and I mentioned a paper from Oxford on capsaicin, I also mentioned a paper from UWE, I think it was on glycerol in wine. Those papers today are all finishing with basic calibration curve and raw signal. Well, look, here we are. I've got the raw signal. The data pipe in the cloud called Julie. So I sent the data in real time to the cloud. It's opened up an analysis window. It's found the peak height there. It's reported the peak height. It put the peak height into concentration using those calibration factors. And bang, it's on my phone at the same time as well. That's all it takes to go from TRL3, which was a lab experiment, to TRL7 or something that I can actually deliver to real people. Because real people, I mean, these are food scientists, food technologists, for example, or doctors and clinicians. These are intelligent people. They just don't want to see your voltammetry or your amperometry, etc. So I did the demonstration in order to give context now to everything else I'm about to say. So I did a demonstration of sensor to cloud. So when you read Richard's paper, he finished with calibration curve, when in fact what we ended up doing was translating that onto this platform. And now we've actually delivered it to hundreds of people around the world who are now using it for actually food quality testing. And so what you can see is it literally is the scientific paper that they originally authored, but now actually it's a product that we can sell. So if you're developing an assay and you think, if you're using things like screen printed electrodes, fairly small potentiostats, and you have a real world application, then I would strongly suggest that you can actually bring these things together. Um, um, and somebody's asking here, are we going to do a multi-channel version of this? We are going to do a multi-channel version of it. We are with, we at ZP, we've got a mix of clients, a lot of academics and then a lot of kind of large, well-funded companies. And so on the well-funded company side, we are actually definitely doing a multi-channel version of this as well. It's quite a long conversation, actually. If you've got a roadmap, in life, if you can get to market with one test, get to market with one test. Some markets, so for example, sexually transmitted diseases, the standard of care is actually to do two or more infections at a time. So there you may need a multi-channel analyte, but don't always start with complexity in mind. Start with you can always get to complexity, but you imagine yourself on a sort of 10-year journey where you kind of have your first product, your second product, your third product. I mean, at Zimmer Peacock, we're quite well known for glucose sensing. Well, the glucose sensing that we do today, it actually looks like this. This is a wearable biosensor, but we didn't start with this. So yes, we can do multi-channel. We do have a multi-channel that we give into projects, but I would also say to everyone, start simple and get complex with time. So what I showed you here was a cloud-enabled, Bluetooth-enabled potentiostat that took the screen printed electrode. What I showed you was it was a 50 microliter drop that we put on the sensor. What I showed you was that we have a app, and I will show you in a minute that you can download this app off the Google Play Store or the Android App Store. And by using QR codes, you can actually change the target, what this app will do. Do you want to do electrochemistry? Scan the QR codes for amperometry, cyclic voltammetry, open circuit potentiometry, linear sweep, EIS, etc. Or develop your own code and your own QR code. It grabbed the data, it sent the data to the cloud. We put it through that data pipe, and actually then it turned it using the data pipe, which is something you'll do anyway. If you're doing a PhD or a postdoc, you're basically producing calibration curves and therefore you've got signal versus concentration. You're already doing this. What you're not doing is putting in a cloud system so that you can actually turn those numbers into final concentration. But that with this system, you actually can turn it to final concentration, and boom, you get an answer on the phone that's meaningful to the real person, let's say, or the real application scientist that you're actually trying to help. Otherwise, it's just stuck in, another journal, and it's part of the 25,000 other papers that got published this year as well. So this app that we're using is available on the Google Play Store. This demonstrates that, there's a good robustness to this. It's not a nice idea, when so many talks and webinars are really about ideas. This is actually something you can download. The app is pretty useless to you unless you've got the Sensi or potentiostat, but you can try it. You can try that. By the way, if you're attending this afternoon or this morning, depending on your time zone, this is recorded. I'll send you a recording later on. You can try for yourself. You can download the app. You probably don't have an account, so you'll basically click that button there. just know that when you set up an account through the app, what you're really doing is setting up an account in a cloud system called Julie. So these two parts talk to one another. Essentially, I said earlier on, you are a data scientist. What you really are is a sort of almost like a front end data scientist. And what I mean by that is you're the guy or people helping to grab the initial raw data, and then you've got other people who kind of come in and start adding value to it. The thing about this cloud system is actually you can add the value yourself. You just need to put your calibration, let's say, algorithm in there, and you can turn that into a raw signal. Anyway, that all happens in a system called Julie. Julie's got its own URL. If you download the app and you create an account, just know that you can log into a cloud system at julie.zimmerpeacock.no. The app talks to the cloud. The cloud is where we process the data. If you did download the app, the first thing it's going to want to do, it's going to want to access your camera, and it's actually going to want to scan QR codes. I may just stop for a second there and just show you what I mean by that. I'm just going to turn the app back on. So here's the app. I go done. I click this button here, and it wants to scan QR codes. So no menus. I can just go between different either analytes or different methodologies just by scanning QR codes. You can see that this is really a technology of 2024. Does the potentiostat connect to Bluetooth? It absolutely does connect to Bluetooth. Just FYI, it says device connected. It's connected. This app is connected to this device by Bluetooth. There are no cables involved. The beautiful thing about using the mobile is that, of course, mobiles often have a connection also to Wi-Fi, or if you've got a data plan as well. So the quick answer to your question is yes, it is. It wants to access your cameras because then you can use these QR codes and change target. But thank you for the questions. So QR codes drive it. You can just do amperometry, open circuit potentiometry, impedance spectroscopy, linear sweep cycle voltammetry, square wave voltammetry. And because of the data pipe, you can then actually process data as well into final concentrations as well. I will talk quite quickly. The biggest problem that we've actually had to overcome at ZP, and I would say for the last 10 years, is actually screen printed electrodes. So screen printed electrodes are not a bad way of commercializing and translating research out of the lab. They're pretty good at it. The problem that's going on here is that people have an expectation that screen printed electrodes are low cost. And if you have an expectation for it and there's enough vendors in the market, you will get now the person is asking here, can they check the data in the phone? Amazingly, the data is collected on the phone and it goes immediately to the cloud. So in fact, you're checking the data in the cloud. So having the data in the cloud answers a simple question: where's my data? And your data is actually in the cloud. So it's actually analyzing it and looking at it and viewing it is actually in the cloud, and the cloud system is called Julie. So when I did that experiment earlier on, I'm just answering questions in real time that are just coming through. So the data is actually up here. So you can see the data. This is the second voltammogram. So the quick answer is the data is actually in the cloud. The problem that we were trying to overcome at ZP when we were first launching this was price expectations that on screen printed electrodes, that's met, that people can get low cost screen printed electrodes. The problem we got is that quality is not met. So everyone is actually running around, not everyone, maybe you're not, but a lot of people are realizing that screen printed electrodes are not reproducible, and I'll talk about that now. And this is basically because there's actually more choice than there is demand. So the problem with screen printed electrodes and pricing is often if you want high quality, you're meant to pay a high price. Not meant to, but these two things are kind of, if you pay a high price for something, you generally expect it to be high quality. If you paid, not much for it, you may be not so disappointed when it's low quality. But of course, in science, because this science is a sort of a quantitative effort, we want to make measurements. We need these screen printed electrodes to be a certain quality so that we can actually quantify what's actually on those screen printed electrodes. So we want a high quality, but because this is academia, we actually can't pay a high price for it. And the only way you can have high quality and with a low price, these phones are pretty reasonable, but they're very high quality devices, but they're a low price. How do they manage that? Because of the volume manufacturing. In screen printed electrodes, we have a problem. Zero Peacock is part of the problem. There are easily more than 10 vendors out there in the real world today, easily making screen printed electrodes. We're just one of them, okay? And some of them come and some of them go. Now, the reason they go is because it's actually quite a competitive market because, hey, there's more than 10 vendors in this field. And these 10 vendors are all producing tens, if not hundreds, of designs. And not only are there people making and selling screen printed electrodes in a commercial way, there's actually, academics also producing screen printed electrodes as well. So there's a whole range and suppliers of screen printed electrodes. Easily over 10 people doing this, or 10 companies doing this, plus all the screen printed electrodes. Right. So they're asking about the carbon screen printed electrodes. I'm going to talk about carbon screen printed electrodes at the moment. What might sometimes the quality of our carbon screen printed electrodes, I think, is actually really high. But if you've got a problem, drop me a line. What I want to say is we've got 10 vendors. They're all producing 50 products each. That means there's over 500 products available to the market. So there's a problem with choice. How many screen printed electrodes do you think are used per year in the R&D setting? How many of these are produced in the R&D setting? And I would actually say there's not more than 1 million experiments being done per annum. So when you saw me earlier on do that test, how many tests like that do you think are happening in the academic laboratories per year? I would strongly suggest that actually there's not more than, a million. No way there's more. Well, no way is a strong term. There's not more than a million experiments, and actually I think a million is actually overstating it actually. Now that 1 million experiments are probably being distributed across 500 products. If you divide 1 million by 500, you get 2,000. Now I want to hold up this sheet, in fact, and say this. You see this sheet? This sheet contains 300 screen printed electrodes on it. This means that if the 1 million screen printed electrodes that are probably being sold into the R&D market per year are being evenly distributed across 500 products, those products are only selling in about the level of 2,000. Now, I know it's not evenly distributed, but what I'm saying is that actually 7 sheets could probably be producing all the electrodes that one particular product would need in a year in order to fulfill the market need. So such a low volume of manufacturing is actually the problem, because when you've got low volume of manufacturing, these SPEs are being manufactured, they're being put on the shelf, they're left to age. It's only high volume that drives low price and high quality. So at ZP these days, we're trying to get to a high quality at a low price, but we're doing it by actually if you come to us, we will say, this is our latest screen printed electrodes called the 501 carbon. The reason we went to this is because we had to bow to pressure in the end. And in academia, lots of people actually like to pipette. And so it's easy to pipette obviously onto a circular electrode as opposed to a rectangular electrode. But even though we carry actually quite a few products, unfortunately, we do say to people, if you come to us, please use one of less than a handful of sensors. They're made of carbon, or they're made of gold, or they're made of platinum. So we appreciate that. Gold electrodes work quite well for self-assembled monolayers, which is quite popular. Platinum electrodes work quite well for peroxide enzymes, or peroxidase, I should say rather. And carbon, I'm generally quite a fan of carbon electrodes because they're low cost. So what I'm saying here is, rather than offering people tens of different designs, we actually just we try to limit it to 5. Now, the reason we try to do that is because it means that we are producing screen printed electrodes in high volumes. And if you can produce something in high volume, then you can generally offer it at a good price and a good quality because you actually have high volumes. What's actually happening in the world is that people will say, oh, I want this particular design, or, and they'll, yeah, sure, the vendor will give you that design. But what they won't tell you is, I hardly produce it And because I hardly produce it, the price is low. I hardly produce it, and actually the quality or the reproducibility is not that high. Now we do put a lot of effort into reproducibility. Um, People are using the wrong metrics when it comes to screen printed electrodes. Sure, at Zimmer Peacock, we can test our electrodes with ferricyanide, and we can demonstrate that our peak height versus the square root of scan rate is linear. But that only doesn't tell you much about the electrode. It actually tells you just about the diffusion of that molecule. So we do find ourselves kind of being asked, "Oh, what's your linearity with ferricyanide and stuff?" And it's like, well, of course we can meet that linearity, because that linearity is all about the diffusion of that molecule. It's not so informative about the electrode. What's maybe more informative about the electrode is the peak-to-peak separation um, between the oxidation and the reduction peak. So with ferrocyanide at low scan rates, yeah, we get good to peak separation, which then diminishes once we go to like 1 volt per second. Then in fact, even at 1 volt per second, it's still 117 millivolts, which is pretty good. But it's the wrong metric. Now, I'm kind of interested in one of the questioners actually, because the thing that we've really worked upon is reproducibility. Now, you saw me do that demonstration earlier on, and if you watch any videos from ZP, you'll often see that we don't use calibration. Why is that? Because we don't want to calibrate. The reason we get away with it is because we think that these screen printed electrodes are really reproducible. Now, the reason we know they are is because we measure them all the time. Why? Because we use them all the time. Why? Because we put them in our customer projects and we put them in our own products. So ZP has a real interest in making sure that screen printed electrodes are good quality, because the first people to know whether we're not reproducible is not you, it's us. And it's actually some of our end users that are using it in products. So our screen printed electrodes, I think, are reproducible. It means it's no calibration. It means that we make simpler assays. Simpler assays means it's easier to commercialize. And if it's easier to commercialize, then we can find it easier to actually have impact. So I started this lecture by saying this is a lecture for academics. We want to encourage impact of academic research. Most academic research finishes with a scientific paper. And a part of that then is, this pretty cool little potentiostat that we now have. But this potentiostat has to work hand in hand with our screen printed electrodes. And so reproducibility is something that we've actually put quite a lot of effort into at ZP. If you're not getting reproducibility with our screen printed electrodes, then drop me an email and put some data in there, and we'll try and have a look at that. Now, reproducibility is not just something that comes by accident. What we're doing is, we are testing all of our screen printed electrodes, not all of them. We're testing every batch by cyclophotometry, making sure that, we have nice CVs, and making sure that our peak, what we're actually doing is checking peak height and making sure that there's a consistency in peak height. So here we've got a relative standard deviation of 6%. Later on in the batch, we check again, and we got a relative standard deviation of 5%. Later on, we check in the batch, and we got a relative standard deviation of 6%. So we're always making sure that we got single-digit relative standard deviation on the peak height in our voltammogram. So we check it by electrochemical method. We do it at quite high volume, and we do it because we need them to be good, because we're using them in our own product, which actually makes us quite unique. I always put the analogy, when you're using ZP technology, it's like going to a restaurant where the chef is eating in his own restaurant. Most actually producers of technology, they produce the technology and they use the technology, but they're not really using it. We use it in our own products and with our own projects. So it means that we're very quick at developing assays. Why is that? Because actually our screen printed electrodes are really reproducible. So we don't have so many outliers that I suspect that 30% of experiments are actually just discarded because you call them outliers, and you suspect that the screen printed electrodes are the problem. So we don't suffer that. So we're basically 30% more efficient than most people when doing this kind of development work, because the electrodes are reproducible. In the end, the problem that we're trying to solve is this: that there you are in your lab, and you can bring some technology to technology readiness level number 3. Now, you may be using a much smaller potentiostat than this, but we think that part of the problem bridging between academia and real world applications is, we think part of the problem is that the instruments that people are using are scientific instruments. They've got most potentiostats on the market have at least a 20-year heritage on them, which means that they're really just lab instruments. Very complicated. It's good to have complicated software, but the software is all focused on actually getting you the raw signal, whereas actually our system is focused on getting the raw signal and then processing the raw signal into an actual final concentration. And it's the last bit into a final concentration that everyone is really forgetting. So we would rather that people are actually doing their R&D on something that looked like a product. Now, when I say something, you know, people are not daft. Of course, I'm biased. I'd like that something to be the platform that we're doing at ZP. But this platform has been sincerely developed over the years, because one of the first paragraphs we wrote on the website was, we see there's a lot of great research going on in academia, but it's not translating into products. And governments and funders recognize this as well. They call it the valley of death. And what they've been doing is just throwing money at this over the years to try and close the gap between research and commercialization. And we say, no, you can close the gap actually just by using instruments that actually can take you onto the market. And one potentiostat that is designed to take you onto the market is the Sense It All potentiostat. Super biased, you have to take that, etc. I've just been asked what's the new price for this. So the new price for this is actually, I think it's about 1,600 euros. Now, so it's probably fairly competitive with what's already on the market. And of course, it's not only a potentiostat, but it's also the capability of going out of the lab and into the real world. So this problem about TRL, most research saying is that TRL3 is a 24-year-old problem easily. We think we can fix it by giving a better potentiostat. So we call it Sense It All. And it's really designed to actually, eventually you can actually generate your own QR code, which all these fields are actually editable. So imagine you're starting a company, or imagine it's your own lab. All the colors, all the names are all editable fields. And so in fact, you can end up generating your own QR code. So the app gets reskinned into what you want it to be. So the final goal of ZP is, it can also be used for EIS as well. So there was just a question that's coming through in the live chat as well. So I'll just do a quick demonstration of that. I really quite like EIS. Electrochemical impedance spectroscopy is, it's a sensitive technique, which is a strength and a problem. If you're having problems with EIS, by the way, I always think square wave voltammetry is a nice compromise. I think these are two of the most sensitive techniques. And if you have a binding assay, then I can appreciate that those are two very good techniques. So the dream at Zimmer Peacock is to get as many companies or as many academics to market in the shortest amount of time. Too many people spend 5 to 15 years trying to commercialize, and at the end of which they're not successful. If you spend 5 years, 10 years, or 15 years, and in the end you're not successful, that's a big chunk of your productivity in your career. So fail fast. You can appreciate here that if you did 3 years of a PhD using this potentiostat, at the end of it, you could actually imagine yourself actually launching something. So, biased opinion, of course. We did do so what I did do was then a sense of the cloud demonstration. As you saw, the data went to the cloud. So let me just do a quick summary. I really wish you very good luck in whatever research you're doing. If it's point of care, point of need diagnostics, then I think we've got a good potentiostat for you. If you're having problems with our screen printed electrodes, drop me a line, because we really put a lot of effort into reproducibility. And if there was a real problem, then before you knew, ZP would know, because actually we use them so much. This is a cloud-enabled potentiostat, and no more laptops, smartphones only. It's no menus. We're just using this QR code. And I genuinely think that if you do a scientific paper on a standard potentiostat, you will finish with a calibration curve and raw signal. I have demonstrated to you today, you'll get a recording this, you can actually put your calibration equation into the data pipe. Your raw signal will go to the cloud. It goes through the data pipe, comes back as concentration. Boom. You're actually got yourself something that's much closer to a product. And therefore, this kind of chasm between oh, well, I just do research and I'm never going to leave the lab, actually closes because the excuses, well, the barriers is a better word, actually just diminished. And the barrier at the moment is, I think, screen printed electrodes and I think the potentiostats that people are using. Now, we also hope that it gives it a better experience for education and also just in the research as well. So I'm just going to finish up with that. Now, I've got a son, he's going off to soccer practice now, football back in Europe. So I'm going to have to go and do that. But I hope this is useful. You'll expect an email out for me in about 4 hours from now when I get back. And if you've got any questions, essentially don't hesitate to reach out to us. Okay, thanks for the questions as well. I do appreciate the feedback. It's good. Okay, take care, guys. Thank you. Bye bye.